Hello, I just want to take a little time and go over some of the material you looked at in this topic, in topic 3.2, looking at the types of solids. So hopefully you've had a chance to work through everything and go over the material. The big thing I want to point out is just our types of solids, some things about network covalent, and some of their properties. So as you're starting to categorize these, in the last unit, the first topic in Unit 2 was identifying if something was ionic, covalent, or metallic. That is basically going to be your first thing you're going to do with these as well. You're going to decide which type of bonding they have. So you'll notice for ionic solids, we've got metal, non-metal. And then for our molecular solids, that one is your covalent chemicals, and so are network covalent. So that's the one where we're going to have to decide what the difference is between those. So those are all covalent. And then down here, your metallic solids are metallic bonding. So this is where we have the sea of electrons, all of that. You'll notice, oh no, I don't have that here. Typically when we look at lots of diagrams of ionic solids, we'll also see those positives and negatives placed on our atoms as well. So our difference between network covalent and a molecular solid. In a network covalent, you'll notice that all of the bonds between these are solid. So every single atom is covalently bonded to the other atoms. So we get this giant network, kind of like a big web of all of the atoms stuck to each other. Whereas in molecular solids, we have individual molecules. So if our formula is N2, then each of these little N2 pieces is a separate nitrogen molecule. And those molecules are then attracted to each other through intermolecular forces. So that might be the hydrogen bonding, the London dispersion, dipole-dipole. You can see that here we've got the little water molecules, right? All those individual ones, and then they're attracted to each other. So the dotted lines are the attractions, okay, between separate molecules. And the formula tells you what the molecule is. You'll notice here in our covalent network solids, this one has a formula, but it's just that repeating pattern. We've got just carbon atoms, just silicon atoms. These covalent network ones are very rare, all right? There's not that many of them. So let's take a look. Oh, mine printed very odd. Okay. When we look at this part, just to check this part, the bonds or forces that are broken upon melting are the forces that are holding them together. So ionic solids, what we're breaking when we melt it are the ionic bonds. And so when they are separated, we have ions. Those are the pieces that we have. In molecular solids, we are breaking the intermolecular forces, and we have molecules left over. In covalent network, we are breaking the covalent bonds, and we would have atoms left. We're going to separate all the atoms. And then metallic, we're breaking the metallic bonds, and we would have atoms left. Okay, so molecular solids are held by intermolecular forces, and we are left with molecules. So we're keeping the bonds together, we're separating the attractions. Everywhere else, we're actually separating the atoms from each other. Okay, so that's the difference with these ones. And that's what's going to happen when we're like, this is what we would break when we're melting or boiling these substances. Okay, when we melt or boil them, we are breaking these forces, these bonds or attractions, depending on the type of substance, and this is what they separate into. So for instance, a molecular solid like ice, water, breaks apart the hydrogen bonds between the molecules to then give us separate water molecules. So if we have liquid water, it's going to change into water molecules when we boil it. Okay, they're still all water. And then the biggest thing we see here is that our network covalent, a piece of data that sets them apart is the amount of energy it takes to actually melt them. They have the most extreme and highest melting points out of all substances. Okay, so when you're looking at data, if we're trying to decide if a substance is either molecular or network covalent, if we've narrowed it down, since they both involve covalent bonding, the big difference is their properties. These are very weak forces because they're just the IMFs holding them together, whereas these are bonds holding them together. So we've got intermolecular forces versus bonds that we're breaking, okay? And you can notice in general, it's harder to break bonds than it is to break intermolecular forces, okay? So that's something to think about. Otherwise, usually it's easy to pick out what type it is because we can look at the type of bonding. But that's what can set these two apart if we're given data. Similar here. So we've got some melting points, we've got some enthalpies, and we're trying to decide the type of solid. And then they give conductivity. Conductivity is another thing we can test for. So, as a solid, the only type that is conductive is your metallic. Okay, metallic substances are conductive as a solid. They conduct as a liquid. Okay, they can always conduct, but they do not dissolve in water. When we're looking at our covalent networks, those generally are not conductive. Our covalent substances are not conductive in any state, but our ionic ones are when they are melted, or if they are dissolved, conducted as an aqueous solution. These ones are Na because they don't dissolve, okay? They're insoluble or only slightly. So ionic compounds, if you separate them into their ions, so we separate sodium chloride salt into sodium and chlorine by either melting it or dissolving it in water, then it can conduct electricity through that, okay? And then metals, they're not soluble, so this wouldn't apply, but they're conductive as a solid or a liquid. So it's another piece that sets those apart. Wanted to look at your last part, or not last part, but the practice on this and show you guys how this chart works. So we're given a whole bunch of chemicals on the left. We are putting 1 to 3 check marks, okay? So first thing, you're going to decide if the chemical has covalent, ionic, or metallic bonds, okay? If it's ionic or metallic, you get 1 check mark just in that column. If it's covalent, then we're going to decide which type of solid is it. Then, if it's a molecular solid, we're going to decide what kind of intermolecular forces it has. I want you to check all possible intermolecular forces, not just the strongest one. Now, I want to talk about network solids a little bit more. They're very rare, like I said in the first part. A type of network solid is a diamond. Okay, diamonds are made of just carbon that's very organized. So pure carbon, pure silicon, pure boron, or silicon dioxide are really the ones you're going to see. Maybe a combination like boron and silicon mixed could create a covalent network, but they're very, very rare. Okay, that's it. Okay, so you could go down this list and go, oh, I don't see any yet until I get to number 18 and I get SiO2. So in that one, I'm going to check that box, network solid, and that's it. Okay, so they are very, very rare. All right, so let's just look at this one. We got NH3. We've got 2 nonmetals, so that's going to put us in the covalent section. It's not a network solid, so that's going to put us here. So then we're going to decide what kind of intermolecular forces it has. Every molecular solid has London dispersion forces. And then you ask, is it polar? Yes. So it can have dipole-dipole forces. And then you ask yourself, can it hydrogen bond? We've got N bonded to H, so yes, it can hydrogen bond. All right. So let's look at another one. We've got krypton. So krypton's just an atom, a single atom. So we have less bonding happening, but it is a non-metal. So we'd be looking at this area. It's not one of our network solids. It's not on our list. So it would have to be a molecular crystal. So when krypton atoms, or if they can be condensed into a solid, we're going to have one of these types. Or we're going to have some intermolecular forces between the atoms, basically. Now, a single atom cannot have a dipole, but it can have London forces. So that's going to be our krypton. So it's a molecular solid or a molecular crystal with London dispersion forces holding the atoms together. All right, we'll do another one. I'm going to come down here. Let's do NaCl, right? So sodium and chlorine, we've got metal and non-metal. So that is going to take us to our ionic column because we have metal, non-metal, and we're just going to check that box. That's all you need for those, okay? So it's like a little decision tree situation that we're figuring out for these, okay? So we want to think about what type of element they are, metal, non-metal, that sort of thing, and help us through these. Remember, we've got non-metals over here, metallic, we've got metals. We might look for the word alloy. And ionic, we have metal plus non-metal happening there. Okay, so hopefully that helps you work through this. And then there are some, is this the previous page? Oh, that's the previous page. Okay, so otherwise that hopefully should help you through those and get you started on that. All right, let me know if you have any questions.